What if I told you that you're looking at a $12 million personal spacecraft? That's right. A single NASA spacesuit costs more than a luxury mansion, and it has to keep you alive in an environment where your blood would literally boil in 15 seconds. But here's what blows my mind. In 2025, NASA and Axiom Space just completed testing on a revolutionary new spacesuit that can keep astronauts alive for 8 hours straight at the lunar South Pole, where temperatures swing 500 degrees Fahrenheit between sunlight and shadow. How does a suit even do that? Let me paint you a picture of what space actually does to the human body. Without a spacesuit, you'd lose consciousness in 15 seconds from lack of oxygen. Your blood and bodily fluids would start to boil, not from heat, but because there's almost zero air pressure. Your tissues would expand, or your skin would stretch, and you'd be exposed to radiation levels that would cook you from the inside out. Oh, and the temperature? In direct sunlight, you'd experience 248 degrees Fahrenheit. Move into shadow? Instant drop to negative 148 degrees. That's a 396-degree temperature swing. And NASA's new spacesuit, designed with Prada, yes, the fashion brand, has to protect astronauts from all of this while they bend down, pick up rocks, and conduct delicate scientific experiments for 8 hours straight. But here's the truly mind-bending part. In July 2025, astronaut Koichi Wakata became the first human to test the new suit underwater in NASA's Neutral Buoyancy Laboratory. And they discovered something that's revolutionizing how we think about space exploration. So how does a modern spacesuit actually work? And the answer is more incredible than you think. Before we dive into the engineering marvel that is a spacesuit, you need to understand the problem it's solving. Let's talk about pressure. Here on Earth, we live at the bottom of an ocean of air. The atmosphere presses down on us with a force of 14.7 pounds per square inch. That's 1 atmosphere of pressure. Your body is perfectly balanced for this. Your blood, your tissues, your lungs, everything expects this pressure. Earth's atmosphere is 78% nitrogen, 21% oxygen, and 1% other gases. That 21% oxygen at 14.7 pounds per square inch gives us exactly what we need to breathe. Our bodies have evolved for millions of years in this specific environment. Now, space has essentially zero pressure. It's a vacuum. If you tried to breathe Earth's normal air mixture in a spacesuit at low pressure, you'd experience hypoxia, dangerously low oxygen levels in your blood. It's the same thing that happens to climbers on Mount Everest. Your body simply can't extract enough oxygen. So here's the engineering challenge. NASA's spacesuits operate at just 4.3 pounds per square inch, less than 1/3 of Earth's atmospheric pressure. To make this work, they use 100% pure oxygen instead of our normal air mixture. At 4.3 pounds per square inch with pure oxygen, your lungs get the same amount of oxygen molecules they'd get breathing regular air at sea level. But this creates another problem. If you go from breathing normal air at 14.7 pounds per square inch inside a spacecraft to breathing pure oxygen at 4.3 pounds per square inch in a spacesuit, the nitrogen dissolved in your blood and tissues can form bubbles, just like opening a shaken soda can. This causes decompression sickness, also called the bends. It's excruciatingly painful and potentially fatal. The solution? Before every spacewalk, astronauts must pre-breathe pure oxygen for several hours. This gradually eliminates nitrogen from their bloodstream. The International Space Station actually reduces cabin pressure to 10.2 pounds per square inch before spacewalks to speed up this process. This is where things get strange. Because modern spacesuits aren't just pressure vessels. They're miniature spacecraft packed with technology that has to work perfectly every single time for 8 hours straight, in the harshest environment imaginable. And the new Axiom-U suit, being developed for NASA's Artemis 3 mission, it's changing everything. What I'm about to reveal will completely change how you think about space exploration. See, the engineering behind these suits is absolutely mind-blowing, and the testing they're undergoing right now in 2025 is uncovering capabilities we never thought possible. Hit that subscribe button because we're covering every major space breakthrough as it happens. And trust me, what's happening with spacesuit technology in 2026 is straight out of science fiction. Let's go back to where modern spacesuits began. The year is 1961. Alan Shepard is about to become America's first man in space, and he's wearing a silver pressure suit designed by Russell Colley. It's essentially a modified high-altitude flight suit. Basic, but functional. Fast forward to the Apollo program. NASA engineers faced an unprecedented challenge: design a suit that could protect astronauts on the moon. The suit they created was revolutionary, and it had 13 layers: nylon for structure, neoprene-coated fabric to hold pressure, 5 layers of aluminized mylar interwoven with Dacron for heat protection, Captain for additional thermal insulation, and Teflon-coated cloth on the outside for protection against tears and punctures. The Apollo suit weighed about 180 pounds on Earth, but only 30 pounds on the Moon thanks to lower gravity. It included a portable life support system, a backpack containing oxygen tanks, carbon dioxide scrubbers using lithium hydroxide, cooling water, a radio, and a battery pack. Astronauts could operate independently for about 4 hours. But here's where the story gets interesting. In 1981, NASA developed the Extravehicular Mobility Unit, the EMU, for the Space Shuttle program. This suit was designed to be reusable. Instead of custom-fitting each astronaut, it used modular components that could be mixed and matched. The suit operated at 4.3 pounds per square inch with pure oxygen. The EMU was supposed to be used for maybe a decade. It's now been in service for over 40 years. That's right. The suits astronauts are using on the International Space Station today were designed when most of you weren't even born. They're approaching the end of their operational life, with parts wearing out, seals degrading, and technology becoming obsolete. Enter Axiom Space. In 2022, NASA awarded them a contract to develop next-generation spacesuits for the Artemis program. NASA provided all their research and design work on the XEMU, the Exploration Extravehicular Mobility Unit, and Axiom took it to the next level. Then something unexpected happened. In 2024, Axiom partnered with Prada, the Italian luxury fashion brand, to help design the suit's outer layers. Engineers from both companies worked side by side, combining aerospace engineering with advanced materials, science, and ergonomic design. In October 2024, they revealed the AXIOM-U, Axiom Extravehicular Mobility Unit. And in July 2025, the moment of truth arrived. Astronaut Koichi Wakata, Axiom's chief technology officer and former JAXA astronaut, stepped into NASA's Neutral Buoyancy Laboratory, one of the world's largest indoor pools, 40 feet deep, containing 6.2 million gallons of water. He was wearing the Axiom-U spacesuit. The NBL simulates the microgravity environment of space by using water's buoyancy. For 6 hours, Wakata tested the suit's mobility, planted an American flag on a submerged lunar surface, used geological tools, and performed complex maneuvers. 2 NASA spacesuit engineers also donned the suit for additional testing. So how does this incredible machine actually work? Let me break it down. The pressure garment. The innermost layer is a gas-tight bladder made of urethane-coated nylon. This holds the 4.3 pounds per square inch pure oxygen atmosphere. Outside, this is a restraint layer made of dacron that prevents the bladder from ballooning like a balloon. The suit must maintain pressure while allowing the astronaut to bend joints, a massive engineering challenge. Thermal protection. The AXMU features multiple insulating layers. In direct sunlight at the lunar South Pole, temperatures reach 260 degrees Fahrenheit. In permanently shadowed craters, it drops to negative 280 degrees. The suit must handle both extremes, and, according to specifications, it can withstand the coldest temperatures for at least 2 hours. The Portable Life Support System, PLSS. This is the backpack. It's the heart of the spacesuit, literally a personal spacecraft. Inside this compact package, first, the primary oxygen regulator maintains 4.3 pounds per square inch suit pressure from tanks holding oxygen at over 1,000 pounds per square inch. The new variable pressure regulator, the first designed in over 40 years, can electronically adjust pressure for different mission phases: pre-breathe, EVA operations, airlock procedures, and even emergency decompression sickness treatment. Second, carbon dioxide removal. Astronauts produce about 1 kilogram of CO2 per day. The AXMU uses a regenerable carbon dioxide scrubbing system, a major upgrade from old lithium hydroxide canisters that had to be replaced. This new system can be recharged, allowing for longer missions. Third, the Liquid Cooling and Ventilation Garment, LCVG. Underneath the spacesuit, astronauts wear what looks like long underwear laced with thin plastic tubes. Cool water circulates through these tubes at about 55 degrees Fahrenheit, removing body heat. A sublimator in the PLSS uses the vacuum of space to evaporate water, which carries away excess heat. It's incredibly efficient. Fourth, the ventilation system. A fan circulates oxygen at 6 cubic feet per minute through the suit. The flow is carefully designed. Fresh oxygen enters at the back of the helmet, flows down over the astronaut's face, and is drawn out from the extremities. This ensures the astronaut always breathes the freshest oxygen while removing exhaled CO2. Fifth, communications. And the suit includes a 4G/LTE communication system with voice commands. Astronauts can talk to each other, mission control, and even control suit functions with voice. Sixth, the power system. Everything runs on rechargeable batteries, providing enough power for 8-hour EVAs. The helmet and visor. Here's where Axiom's partnership with Oakley comes in. The visor system includes a 2-part deployable visor for harsh lighting conditions and is coated with 24-karat gold. Why gold? It has natural properties that filter harmful portions of sunlight, particularly ultraviolet radiation. In space, this protection is critical. Onboard diagnostics. The suit includes sensors monitoring oxygen levels, CO2 concentration, temperature, pressure, water flow, battery status, and even the astronaut's heart rate. If something goes wrong, the system alerts the crew immediately. But here's where things get really interesting. Just when you think you understand how spacesuits work, engineers discovered something unexpected during testing. The biggest challenge? Mobility. When you pressurize a suit to 4.3 pounds per square inch, it naturally wants to stay rigid, like an inflated balloon. Every joint becomes stiff. Bending your elbow requires fighting against 4.3 pounds of pressure per square inch over the entire joint surface. Multiply that across every joint, and simple movements become exhausting. The Apollo astronauts described moonwalking as incredibly tiring. They could bend their knees and elbows, but it took significant effort. And they certainly couldn't kneel down easily, a major limitation for collecting rock samples. The AXIMU solves this with innovative soft and hard joints. Our certain joints use bearing systems that allow rotation with minimal resistance. Others use carefully designed fabric folds and pleats that enable movement while maintaining pressure. During the July 2025 NBL tests, engineers specifically evaluated the suit's ability to let astronauts kneel, crouch, and perform delicate tasks with tools. But there's a competing approach that's generating controversy. In 2006, 5 North Dakota colleges developed an experimental spacesuit operating at just 1 pound per square inch differential pressure. At this low pressure, mobility improves dramatically. The suit is much easier to move in. The entire prototype cost $100,000 compared to NASA's $12 million flight-rated suits. So why doesn't NASA use low-pressure suits? Safety. At 1 pound per square inch with pure oxygen, you're right at the edge of providing adequate oxygen partial pressure. Any leak or malfunction becomes immediately life-threatening. NASA's 4.3 psi standard provides a margin of safety. Then there's the question of sizing. Historical NASA spacesuits accommodated maybe 40% of the population. They simply didn't fit smaller or larger astronauts, and the rigid components made customization difficult. The AXIMU is designed to fit anyone from the 1st to the 99th percentile of human body sizes. This is revolutionary. It means the first woman walking on the moon won't be restricted by suit availability. And here's the twist that's changing everything. In January 2026, NASA completed critical design review preparations for the AXIMU, but they're also working with Collins Aerospace on a competing design for ISS spacewalks. And the future of spacesuits might not be one universal design, it might be specialized suits optimized for different environments. So here's what I genuinely want to know from you. After seeing how these suits work, which feature do you think is most critical? Drop your vote in the comments. Option A: life support, oxygen, CO2 removal, and cooling systems. Option B: pressure and thermal protection, surviving extreme temperatures. Option C: mobility, being able to actually move and work effectively. Option D: communications and diagnostics, staying connected and monitored. I'm genuinely curious what you think is the make-or-break technology, because engineers are actively debating these priorities right now as they design suits for Mars missions. Your perspective matters. Maybe you'll identify something they haven't considered. And the implications of modern spacesuit technology extend far beyond just NASA missions. These suits are teaching us how to create sustainable life support systems for extreme environments. First, the Moon and Mars. The Artemis 3 mission, scheduled for mid-2027, will land the first woman and the first person of color on the lunar surface. They'll be wearing AXIMU suits, exploring the South Pole for up to 8 hours per EVA. The data gathered will inform the next generation of suits designed for Mars, where astronauts might need to work outside for weeks or months during exploration missions. Second, commercial space. Axiom Space isn't just building suits for NASA. They're creating a commercial market. Private astronauts, space tourists, and commercial space station crew will all need spacesuits. The AXIMU architecture is designed to be adaptable for multiple customers and mission profiles. Third, terrestrial applications. The same technologies that keep astronauts alive in space, advanced thermal management, closed-loop life support, compact power systems, have applications in deep-sea exploration, hazmat response, firefighting, and even medical equipment. The regenerable CO2 scrubbing system developed for spacesuits is already being studied for use in hospital ventilators. Fourth, AI and automation. NASA's Suits Challenge, Spacesuit User Interface Technologies for Students, is recruiting university students to design augmented reality interfaces, voice assistants, and AI systems for future spacesuits. Imagine a suit that can diagnose its own problems, guide astronauts through procedures, and even make decisions about consumables management. And finally, this connects to all of us. The engineering challenges of keeping humans alive in hostile environments are teaching us fundamental lessons about sustainability, resource management, and life support systems that we'll need as we expand beyond Earth. Every spacesuit that keeps an astronaut alive for 8 hours is a proof of concept for permanent off-world habitats. But here's the hopeful part. We're getting better at this every single day. The Axiom-U completed its first thermal vacuum test in early 2025, exposing the suit to the actual temperatures and vacuum of space. It passed with flying colors. NASA's partnership with commercial providers like Axiom Space and Collins Aerospace is accelerating innovation. Multiple companies competing means better designs, faster development, and ultimately safer, more capable suits. The Nancy Grace Roman Space Telescope's planned 2027 launch isn't just about astronomy. It's part of a broader push toward sustained lunar presence that will require dozens of spacesuits operating regularly. We're moving from spacesuits being rare, precious equipment to becoming standard tools for space work. And the lessons learned from the Axiom-U will feed directly into suits for Mars missions in the 2030s. Engineers are already working on suits that can handle Mars's thin atmosphere, dust storms, and longer mission durations. Science is making real, measurable progress. The spacesuit technology being tested right now is orders of magnitude better than what we had even a decade ago. But spacesuits aren't the only incredible technology enabling space exploration. There's the new lunar terrain vehicles being tested right now for Artemis missions. Basically moon cars that can operate for years in permanently shadowed craters. There's the SpaceX Starship HLS lander that will carry these suited astronauts from lunar orbit to the surface. And there's the question everyone should be asking. If a spacesuit can keep someone alive for 8 hours in space, why can't we build similar systems for disaster response, underwater exploration, or extreme environment work here on Earth? If you want to explore these engineering marvels with me, subscribe and hit that notification bell. The future of space technology is being built right now. Thank you for joining me on this deep dive into spacesuit technology. And these incredible machines are more than just protective gear. They're personal spacecraft that represent the pinnacle of human engineering. Every seal, every valve, every layer has been designed to keep explorers alive in the most hostile environment we've ever encountered. The next time you see an astronaut floating outside the ISS or walking on the moon, remember, they're inside a $12 million miracle. Keep looking up. The future of space exploration is closer than you think. See you in the next one.